There we are. All right, let me introduce our next speaker, and it's Adi Chilukuri, who's at ANU, and he's working with Shoaib Akram. Welcome, Adi.
Hi, thanks, Steve. Good morning, everyone. My name's Aditya. You can call me Adi. Today I'll be introducing my work on analyzing and improving the scalability of in-memory indices for managed search engines. So I worked on this project as part of my undergraduate studies at the Australian National Universities under my supervisor, Dr. Shoaib Akram. So let me first introduce my problem. The problem that I was targeting was full-text search. Obviously, it's not only used by Google and Bing, the search engines, but also in social media and retail. And these applications get millions of requests a second, so they really care about throughput. And these applications are latency sensitive because users are incredibly impatient. And increments of 100 milliseconds in latency will lead to measurable drops in revenue for these companies, and that's been found. So, goal for my work is to create a high throughput and low response time system, hopefully one that's better than the state of the art. So we'll see. Okay, first let's talk about how search engines work. The search engine is backed by the base data structure, which is called the inverted index. Inverted index is essentially a dictionary which maps terms or words that appear in a document set to the documents which contain it. It's like a key value store with the values as a list of postings, where a posting is like a 3-tuple of document ID, which defines the document, the number of times the document appears, and where it appears. So, well, there's that. Index sizes increase as data sizes increase, and we want to put them on DRAM for the best possible performance. However, we've run into the problem where DRAM capacity is limited, and if we just chuck it on SSDs, you're going to run into a lot of latency problems at the tail of it. So, well, yeah, that's currently the situation. So what people typically do is you buy just about enough DRAM to store your index as much as possible in the OS page cache. So stored on SSD, and upon index warm-up, you're going to be reading that index and putting it into the operating system page cache. But in a managed language runtime environment, there is also another option. Why don't we just put it in the heap? People don't usually do that because one of the reasons is they're scared of the GC overhead. We're going to make the heap really big, so people don't do that. One more thing I want to talk about was how query evaluation actually works. It's essentially a 2-step process. The first step is, let's say a user query comes in for drop bear. The first thing you'll look up is look up in the term dictionary for the posting lists matching for the words. Then you do some traversal where you do some set operations on the posting lists. You do some scoring and ranking. There's some computation involved. And at the end of the day, you'll get some documents that you can present to the user. So dictionary lookup is fast. Don't worry about it. Dictionaries are small. Don't worry about them. The main problem is posting list traversal because postings are really long and traversal is quite slow, especially with popular queries because the posting lists can get quite long. We also see that it's a sequential access pattern, which is really good. So I actually kind of lied to you. One of the steps that's in the middle of the query evaluation is dealing with the fact that we actually store the index in a compressed format to save precious DRAM. And when a query comes in, you get the posting list, you decompress it on demand, and then you can do all those wonderful posting list operations and get your results. Which leads us to the natural question, like what's the overhead of doing this decompression step? So let's do an experiment where we remove it, and we're going to deal with a uncompressed search index and try to measure what the speed up would be, what the pressure on the memory is. And to do that, we come up with a methodology. We used Apache Lucene, which is a Java search engine library. And pretty much all the code here is existing modulo some changes for bug fixes, etc. But the left-hand side is the baseline, which is the standard Lucene search index. It's stored on disk, brought into the OS page cache during warm-up, and decompressed on fly. The uncompressed index is also part of the Lucene code base. It sits on the heap, and you read the posting list directly on the heap. There's no page cache involved. Okay. Let's run it. What do we get? Interesting things. We get a 37% improvement with the uncompressed index, which is great. And another thing is that the performance improvement is consistent over core counts. So that's not to say that you don't get a bottleneck or slowdown at higher core counts. Search bandwidth, a search requires a memory bandwidth that is not provided by memory. That is still true. But you do get a speed up, which is great. But we need about 10 times more memory. So, okay, what are we going to do with this? We can't put it on DRAM, we don't have enough of it. We need some form of scalable memory. In this talk, we looked at non-volatile memory, in particular Intel Optane persistent memory. But there are some other interesting options, such as leveraging fast storage, like the fastest, the lowest latency SSDs. Can we actually do what we want with that? And the other option is remote disaggregate memory, which is storing memory on a separate server and CPU on a separate server, and there's a fiber connection between them. It's something that's faster than SSD, slower than local DRAM. Could be really interesting. We don't really look at it. So, non-volatile memory. It's essentially a complement to DRAM. It's got high storage, but and it can act like DRAM, so it can act like main memory, but it can also, since it's persistent, act as a storage device and can appear to the operating system as either. And with enough investment, since it's a different memory technology, the storage capacity can scale better than DRAM can. So microbenchmarks show that, okay, depending on some details, it's 2 to 3 times slower. Which leads us to the question, can we place the uncompressed search index on NVM and gain a similar speed up over the compressed index in DRAM that we measured? So to do this, let's create a few different setups. The first two are the compressed and uncompressed, or LPF and DPF setups on DRAM. We've already seen those. I'm not going to explain them again. The next one is the compressed setup on non-volatile memory. We place the index on a non-volatile memory file system, and there's no OS page cache because non-volatile memory is directly byte addressable, so you go directly. And the next one is the uncompressed or DPF system on non-volatile memory. This is done by essentially memory mapping the Java heap onto NVM. Now, one of the things you might have noticed is that there's not just the index on the heap, there's also search objects, which are objects created during search evaluation. It's kind of silly to keep that on non-volatile memory because they're going to be accessed a lot. So how can we best put it on DRAM and not use too much DRAM and put the index on NVM? The method we ended up going for was to chuck it, was to split the heap and chuck it on the young gen. And we do this by, like splitting the heap. There's a flag which allows you to do this. So, and then we sort of play with the young gen size to see what the sensitivity is as well. Okay, so let's look at some results. Okay, just looking at the compressed setup for now. If we just take the compressed index and put it on NVM, there's no actual change to any code that needs to happen. You're only 2% slower. That's pretty crazy for something that's supposed to be 2 to 3 times slower. Okay, we already know this. This is the uncompressed index on DRAM, 37% faster. I already mentioned this. Okay, you put the uncompressed index on NVM and you're only 10% slower than uncompressed on DRAM. And that's still 30% faster than the state of the art. Okay, then we have the hybrid setups, which is to place the young gen on DRAM. And you notice that as your young gen size increases, your systems get faster. That sort of makes sense as well. Okay, but there's some surprising results. I mentioned already we're expecting something to be 2 to 3 times slower, but it's only 30% slower, 10% slower. And before I celebrate, I have to put a meme in there about confounding factors. So is there some weird GC magic going on? Something that could be causing like, an improvement by making something look bad? And the other side is like, can we look into the hardware performance counters and actually see what the impact on memory performance is when we change the memory hardware? Okay. Is GC a confounding factor? Okay, we measured GC overhead for all the different setups. Only the compressed index actually showed GC. That's kind of one of the reasons for that is that with the direct postings format, you have a negligible GC cost. One of the reasons, and the main reason for that is that the old gen typically will only contain the index, which is immutable, and since search is highly generational, if you size the young gen properly, you can ensure that objects created during search will be killed and cleaned before they dirty up the old gen. And one of the things that we try to, one of the other things that we have in the uncompressed index is that there's no pointers in there. It's all primitive arrays, which also reduces scanning overhead. But it's not actually that smart to store it, so we can actually get back to that. At the end of the day, GC is not a confounding factor. Okay, I think in the interest of time, I'm not going to go into too much detail on the full top-down method. I can recommend looking at the paper that Intel Research has released, and there's some detail in my paper as well. But yeah, okay. So let's come specifically to, so on the y-axis on this graph, I'm showing basically like as you dig down into the analysis, we found like the root performance impact of NVM or DRAM on the execution by measuring the percentage of store cycles across the different technologies. So what you find is that, yes, as expected, you have a 2 to 3 times worsening across the technologies in the number of cycles that are stored. And that's the same for multi-core as well. But the absolute value is still quite low. There are a couple of reasons for this. Either the entire index fits on cache, which I God hope does not, or prefetches. Prefetches are doing a really good job. So let's try to figure that out by looking at larger indices. So we looked at the Common Crawl dataset, which is an open web crawl, created some indices, and let's take a look. Okay, so this is the performance data for the larger indices. We go up to 87 gigabytes on the index size, and we find that our trademark system, DPF hybrid, consistently outperforms the state of the art across all the index sizes, and the highest it's 30% better. You actually see a 10% slowdown on the compressed index on NVM. Okay, and then let's go through why that might be. One of the things that's going on is that misses per kilo instruction decreases as the index size goes up. That implies that prefetches are doing a better job as posting lists get longer. So they're just helping us out a lot, basically. And because of that, you're able to hide a lot of the latency of the memory technology because all those graphs are going down as the index goes up, index size goes up. Okay, so basic idea of this talk is that space-time trade-offs are changing, and we need to rethink some of the presumptions we've made 15, 20 years ago about the different memory technologies. I'm not saying that we should store the entire index of everything in uncompressed format on some technology, but you can use it as a cache, and if you decide what's important to you by storing it in uncompressed format on some maybe slower technology than DRAM, you could get a speed up in your application. And for future work, we could look at different hardware technologies. And on the software side, not just index search, but data and analytics applications, key value stores. Yeah, and thank you very much.
All right, thank you, Adi. We have time for just 1 or 2 questions, but I'm sure Adi may have to take questions offline after that. Questions?
If the document base is growing and the index has to be updated, what do you do?
So that's a great question. With updating indices, the way we typically do it is like we create new indices or new segments of the index, which, like, there's been some work on indexing on NVM, which, like, for example, my supervisor did some work on it. Shoaib has a paper on it. But on the search side, like, you just like add more of these segments onto your index, and it becomes like quite a similar problem. Does that answer your question?
You can probably follow that one up offline.
You don't update it on hotspot until the new one.
Yeah. And the other thing, yeah.
Last question. Yeah. Did you try using Intel's memory mode? It's like a hardware-based cache that uses.
No, that's future work. It's really cool. Yeah, that'd be sick.
All right, thank you, Adi, for your amazing piece of undergraduate research work.